Books and other reading materials are all around us. We use them for entertainment, we use them to learn from, and keep current in society. But what all those sources have in common is they all require hands to be used. So what happens when you don't have hands to use these materials? Well, that's the problem our client currently faces. She has been diagnosed with multiple sclerosis and no longer has use of her hands and requires the help of others to operate books for her. Our goal is to allow our client and others like her that no longer have full function of their arms and hands to read books as independently as possible by designing a device that allows for the turning of pages of a book via head movement. We hope to return what they have lost and allow them to regain their hobby. This needs to be done to be able to allow the client to read on her own without the help of others. Our group's first process was to take in the constraints and work on a design that met those requirements. Each member of our group came up with a design idea that we would present to one another. From there, we weighted our ideas in a matrix and found none of them met our goal. However, by combining the designs presented, we could achieve our goal and that it would have the best chance of success, with safety being our #1 priority. After finding a solution, we began drafting parts that would make up our design. This would take a good portion of the classes, but after trial and error, this is the build of our design. The way our design works is a book is placed on the base, and by activation of a switch via head movement, this will activate the first movement, which will turn the belt assembly on the page, creating a lip in the book. Once the lip has been created, the other motor assembly will engage, spinning a disc with a fixed spiral, lifting an arm that will catch the lip of the page and turn it over, and will stop to hold the page for the reader. Then once the reader is ready for the next page, they will hit the switch again. This time the arm will reset first and the process will reset. These timings are achieved through the circuitry. Now that we had our design, we needed an analysis for part of our design. So for our analysis portion, we decided to calculate the spring constant in order to find the spring we require for our application. Since we were planning to use McMaster-Carr to choose our spring, we had to calculate the parameters that would help us narrow down our search. We assumed the belt system would roll without slipping and the spring was stretched to 10 millimeters. By plugging our values into the equation, we get a spring constant of 6.64 Newton meters. With the spring constant, we can properly choose a spring that fits our need. Finally, what did we learn from all of this? We learned that attention to detail is very important, even with the small things that we thought was intuitive. That somebody who is reading your drawings may not have thought of the specific piece to go there. Another important lesson learned of the drawings we found was that showing how all the pieces of your parts fit together, that sub-assembly drawings are just as important as the parts themselves. The most important lesson we found to take away from all this, especially with the ongoing COVID crisis, is how important communication is with your peers. Without communication, it is hard to get anything done, so having very strong communication skills is an asset when taking on challenging problems.